this computer. There we go. Thank you, Connor. So there, you have a couple of options, right? I mean, you could actually use Zoom, just like we're doing, like I'm doing. That would actually be a perfect way to do it. There's an option, there's a program called Loom. There's Screencast-O-Matic. I don't want to turn this into something that is not enjoyable, but I'm trying to give you the opportunity, sort of, the why / the how, right? Did you integrate structure into your project? And so the main focus is obviously in this one, it's the lateral system. So just to keep you, one moment, keep you pointed in the right direction. First thing is trying to keep your cursor. There we go. To give you a heads up, right? Project 3, which would be coming up, right, and number 4, but those are our last two. Right? Those are going to be solo projects, and it's going to be sort of a accumulation of a project 1 and a project 2 together. So something that you'll deal with both the gravity system and a lateral system. So we'll talk about that a little bit on Thursday, but just kind of keep your thoughts on that. You'll have the opportunity, and you'll be doing that by yourself on a project. So I think I will have that ready to talk about on Thursday. Homework 3 is also up if you want to get started on that as well. So I think scheduling wise, I think that gets us in a pretty good spot, hopefully. If you do have any questions, just ping in, or you can obviously get with me after class or by email. So just a minute. There's Christian. Okay. All right. So finishing up this structural selection and creativity, we're going to talk just, in some broad strokes about that. Just some bigger picture issues with that. There'll be some overall review issues as well, sort of polishing you up as you look at project 3 and project 4. So that's really what the main focus of those are going to be, doing the class on a project on your own. And then on Thursday, you want to keep it just in mind, we're going to start cladding, or the exoskeleton of the building. And so we'll start talking about those issues specifically on Thursday. So, all right, that should, I think, get us there. So I would think, like I said, we will be done by about 5. And then, Ariel, just a moment. And then we will have a little bit of a work session. Ariel?
Yeah.
Oh.
Yeah.
You have a question?
Not really.
Oh, no? Oh.
No.
Okay. Your thumb is up. Your blue thumb is shining.
I didn't put it down earlier. Sorry.
Oh, that's a thumbs up. I guess the other one is a hands up, huh? Okay. All right. All right. So key components to structural systems, right? You've got loads, right? Dead load, live load. This little bit of some work on reducing that live load, right? That'll be part of the column design in your project too. So make sure you've done that. And the other thing I'll say it at the end as well, but that handbook, right? The one that's like 35 pages. I don't know what your situation is. That's something I would encourage you to print that thing out if that's doable for you. That's something that you're really going to want at your fingertips as you work through the projects 3 and 4. Or at least I would encourage you to. So, or at least have very, very strong access to that. Right, the superstructure, sort of the gravity load, and then the lateral support system, which is what we've just tried to bring forth with you, right? And then other topics that we're not really going to get into a whole lot in this class, but we do get to as close to the foundation as possible. I mean, we do get some of those ground level forces. And so not just the base shear, but the column, sort of the columns, right? And those shear wall forces. So we literally get right up to the foundation. And this is where the rubber meets the road. I mean, then eventually your structure has to transmit its force from the foundation, and then it gets delivered to the local site, the soil condition. So there's quite a bit there. And then the local geology also gets into some of those seismic issues. But this is obviously, we're more up here. Don't know, maybe we'll get a little bit there at the end, depending on how we're doing. But those are part of the process. So from these functional issues, terms of choosing a structural system. So the spatial aspects, right? Not only are there 2Ds, which, show up in your plans, that's obviously part of your project too. I've asked for, right, one elevation, right, or a perspective to give that 3-dimensional view. And really that deals with the system integration. That can sometimes be a little more challenging to see on a 2D view, but that's the focus of it. You're producing something that has some drawing to it. Ultimately, though, this is a 4D view, because this is a time, this building is going to evolve over time, perhaps changing usage. So keep in mind that this is actually a 4-dimensional issue when you're speaking of usage at a later time, or the functional aspect of it. The loads obviously change when the usage can change. So it's best to take a conservative approach, designing for the largest possible loads over time. Again, this is more general, a little more qualitative thoughts than anything that you'll quantify in a project in here. Also, from a design point of view, just think of seismically thinking in terms of overturning moment, or force is mass times acceleration. So you would generally want loads that are in the building, you want them closer to the ground, just in general, especially dealing with the amount of overturning that would occur. Sometimes, we'll talk a little bit later, is you could end up with a large weight at the roof. You could have some sort of a mechanical device that might need to be up at the roof. So something to keep in mind. Here, I would say you can read this one. And so I'm going to just say, as you read it, reconsideration, right? That leads to re-engineering. And re-engineering is money, but not as much money as building. Sort of construction. So the issues with changing the occupancy and then possible egress or mechanical systems as well. From a circulation point of view, protection of the egress, this is often why you end up with, a very stiff or a core to the building that might be protecting a stairway or an elevator. And a lot of times the creation of that core is you end up with something very stiff from that core perspective. So when you talk about stiffness compatibility, just from a calculation point of view, force is equal to the stiffness times the deflection. Right? And this is just a general equation of a spring. So if we had an element that had a stiffness, right, and there was a deflection in the building due to wind, due to earthquake, and if you had a second element which had a different stiffness, I'll call it K2, and it has the same deflection that occurs. So it's working in harmony or in the same direction as another system. And I'm trying to make the point of this stiff core. Anything that's stiff, that would mean K is very big. So you can see if you have two elements that have different stiffnesses, the larger force would be associated with the stiffer element. So you just have to be careful from a stiffness compatibility point of view. Those routes, the egress routes, the openings that would have to be present within your structural system. And so this kind of the idea of a solid box, right, which versus a box with lots of holes in it. So one might be a little bit more boring, but it would be more, it would definitely have more integrity and wholeness to it than a box that would perhaps be more artistic because there's lots of holes in it or different materials, which definitely would be more artistic. But just the trade-off or the issues with the structural system and those concepts. So that just needs to be weighed appropriately. So like holes in shear walls start to make shear walls, not whole length shear walls. So those want to be to a minimum. Or you want to put your shear wall somewhere else where it doesn't have to have a hole in it. Same thing with diagonal braces, and sort of give a funny example, those diagonal braces, bringing you back here to Cal Poly. If you were to think of the lovely Mustang Stadium behind the old side of the stadium and all the cross braces that are present, and they have lots of pads on them. Perfect way to decapitate somebody, a fan after a game. So just the issue, it's a very bad example of, structural, the structure being the way of circulation to an extent. And so those just need to be thought out ahead of time. I probably wouldn't think, I might be overstepping, but probably whoever the architect was not really looking to have that to be a part of such a memorable part of the stadium. But it is part of our stadium, which I wish we were all there, but we are not for sure. A little bit of site context. I got wrong word. I said must also be considered. Kind of let you look at this. So that second one, the location, the access, the issue with, really the size of an element. I mean, if you need something that's prefabricated as part of your building construction, can you even get it there? And I like that the building site is first a factory for the product of the site. And so, is there space to construct? How must that be taken into account? So here, I mean, natural disasters, tsunamis, let's get them all out there. Volcanoes, tornadoes. So lots of possible natural disasters. Two that we're going to focus on, obviously, are right there. So won't do a huge amount here, but just expose you just things you've obviously heard about. But this would be, do you need to bring in a specialty? I don't know why the pen does that. Crew to construct, right? A regional issue. And then here, obviously dealing with money issues. As I was adding some notes to it, right? I mean, the global economy, right? Dot, dot, dot. Just quite honestly in horrible shape. So obviously life cycle issues as well. So just a little bit here. This idea of a passive energy, a lot of solar, which begins that kind of Swiss cheese effect that could show up in a building, which starts to really break into the structural integrity. I mean, if there are too many holes in the building, so kind of like that box analogy a little bit earlier, the other with the building, with the building system itself, like library, if light fixtures need to be in a certain location, or equipment that needs to be located basically like along the stacks. So that not a very specific location for it. HVAC, and then that's where also, based on that, you can end up with large pieces of machinery on the roof, which obviously gets into a little bit of seismic issue and kind of your last couple of pieces right there. So nothing that we get into from a, you know what, so let me do this. I'm gonna take about a 5-minute break here. Get you back at about 4:35. Give me just a minute here. Sharing. All right. All right, let's see. So kind of making good progress here. This idea of the building envelope is what we begin on Thursday, right? They've got cladding, and we will begin to look at how that is hung, sort of hung on the building. And so just like anything, it becomes something that has weight, and then also mainly the issue of how it's connected. Connections become quite important for a support and for a disconnect from the structural system. So you can kind of read through these, talk about right here about the detailing, the if it's not detailed properly, then it actually will become a part of the lateral system, which would not be intentional. That would not be good. Generally speaking, that a lot of the cladding might be a lot more stiff, which would then end up attracting quite a bit of load to it. And so that's funny or not, but like it's a, the lateral system, it's not it's not an all hands on deck type of thing. The lateral system is going to be designed such that it can function on its own. It does not, cladding, helping, it's not actually what would be happening. So that's where the detailing comes in a little bit. And so the other is, and several details exist, but the thermal expansion and contraction. And so then we will end up dealing with the detailing quite a bit. Just how is the cladding, how is the cladding part of the building system? All right, so we're gonna do a quick review. This is just a general overview, kind of getting you a help a brush up on project 2 if you need, and also just getting you ready for project 3. Second. So you would, let me go a different color here. So I would encourage you, again, I said it earlier at the beginning, but maybe printing out that handbook, right? The 36 pages or so, I believe it would be very worthwhile here coming down the stretch, especially. Those are the notes, if you will, sort of the cliff notes that you just want to keep being aware of as you go through this. Steel framing, just very quickly, beams. This came up a little bit on homework 2, but those want to be at columns. That's part of what the grid spacing, is for. So you'd want to hit the columns with your beams, and then you've got somewhere between 8 and 12 feet spacing in between the beams, and then obviously flowing into the girders. With that, right, with that sort of 10-foot span-ish, 10 feet, right, between 8 and 12, that ends up then with a 6-inch thick deck and infill that would be on top of those steel beams. All right, this keeps coming up quite a bit, the span to depth ratio. That then gives us a minimum depth, right? That deals with some deflection, also with some stability. And then from a strength point of view, then we move into the LRFD loads, our factored loads, right? The 1.2 and the 1.6. Right? And all you're trying to do is find your demand. And then you end up back in the tables in some, right, one of those pages, and you're trying to select the size such that the capacity, right? You always want your capacity, that's what CAP, is always greater than or equal to the demand. So there's your sizing, right? Concrete on page 26. We'll talk just a little bit more about the slabs here in just a second. Got some pictures to kind of talk through a little bit. The difference between like a one-way, some of the one-way and a two-way slab. So this would be a similar, it's very similar actually in if it's a one-way system. It's similar to the way steel is. It's different though. Span-wise, you've got somewhere between 6 to 20 feet, 20-foot max from a span of the slab thickness, right? About L/28. That's all in that handbook. In general, right, there's an 80% reduction when you end up calculating the demand moment. And this comes from the natural sort of continuity of concrete. So that's one difference, that you end up using the factored loads to find the moment. We'll have an example here in just a second. And so you always use 80% of it. Oh, I don't know why it does that. Man, very slowly here. There we go. No. You know what? Just a second. Boy, it really doesn't like this, does it? Okay, you made it. Okay, in the tables. So the demand versus capacity. And just remember, that's where the BH squared over 24. And there are some sort of magical units that show up there. These are all in inches. And then the demand over there is kip. Oh, my pen is going a little crazy on me. Kip feet over there. So from an example point of view, all right, just very quickly, there would be columns. Got a beam right here. There would be the slab span. That happens to be 20 feet. Here's some loads that would be showing up. And from a span perspective, right, for the slab, L/D of 28. So remember your units, that would tell us you'd need about a 9-inch slab to do this, right? There's the factored load. And then the demand on the beam, right? Those beams that were running left, right. So it was 20 foot of tributary width, right? There's the factored load, right? Pounds per square foot times 20 feet. And so you've got your 1/8. You know what? I think I know why it does this now. When my computer starts to run, it doesn't like that. And so that's the demand moment, and there's the 0.8 that would be sitting out there in front, the 80% for concrete. And so then if you'd end up on page 27 for the sizing, and so you're going to cue something that has a capacity greater. So two-way, a two-way slab system, you know, the requires, right, really just a slab thickness, but it requires a square bay. And that deals, the reason is because of the two-way span of the slab. If it wasn't, if the aspect ratio of the bay was not square, then you would have something that would, even if you tried to span it both ways, it's going to predominantly span in one direction. So to use a two-way slab, you need a approximately square bay. They can only be between 20 and 30 feet. There's your thickness requirements. And so the beam spacing is going to end up equal to the girder span in a two-way slab. So here's a quick, just a review of that. Let me get this down a little smaller. And so there would be the two actions, right? And so you can read through all the kind of the way the difference between them. There's the ratio issues, the size of the bay. So there's our one-way on the left. There would be our two-way on the right. And so that, again, why would you choose one over the other? And that could be because of you don't have walls on all four sides. Or again, if you don't have something that would be a square, sorry. There's some variations. So here would be a two-way slab that would have beams, right there. Oops, could be present. Here would just be a flat slab that has no beams present. You may actually then, and you may end up needing a drop panel that would be around where the columns are, the tops of the columns meet. Need something that drops down. That would be for what's the issue of called punching shear. And so the column would want to punch through the slab. So sometimes you have to beef the slab up only at the tops of the columns. Right here would be a waffle slab. And so you see that you've got infill right there around the tops of the columns. So that's because of a punching shear issue, and much more lightweight in terms of you end up with a very, very thin slab, but obviously a totally different structure. So, all three of these would be considered two-way slabs of a slightly different variation. So long span elements, also known as transfer elements. And so you could end up with, right, an engineered truss, a plate girder. On homework 3, you'll have a plate girder that'll show up. I'll give you a table with that. You end up with, with these, you end up with a lot more free body diagrams. They've got a repetitive nature to them, these long span systems. Generally, there's not just one of them. And you have to be able to span between them, right? You have to have elements to span between these engineered trusses. Another option to use, different, would be open web steel joists. And so difference being is that those will end up being very tight spacing, 10 feet, 5 foot, or 10 feet. Those are also in the design manual. So again, options for how you end up with spanning a long span. Just going to leave this here. This is obviously what we've been working on, right? There are 2 base shear for seismic equations, one for short structures, one for tall structures. Generally, if you've got something less than 60 feet, right, you'd only need to use the short equation. You're always going to choose the smaller of these. So it wouldn't be bad if you just did both of them. If you weren't sure, you couldn't remember, you could always do both and just choose the smaller. The reason why for a short period structure, right, you can kind of see this for a short building, you've got short periods. And so period is right down here. So if you put a small number into the denominator, that pumps the whole thing up. So that's, again, we're covered here we're going to choose the smaller of those. So ductility, the ductility factor based on the structural system. And then weight is obviously the dead load. And then we've been over the location of the statically equivalent point load. And that just comes from the triangular nature of the lateral force. Over on the wind side, right, there's again that magical 60 feet. Use constant if it's less than 60. If it's above 60, then you have to use what's specified. And that could be trapezoidal. So on project 2, you pretty much, I've asked for something over 4 stories. So that doesn't mean you definitely would, but a lot of you will. And so you'll end up with a trapezoid. Don't worry, if you didn't, you will end up with one on project 3. So you'll have a chance to do that even if you didn't. And the thing to keep in mind, and I know sometimes this might be sacrilegious, but the way that you find the base shear is you integrate the pressure over the surface area. And so if it's a constant, it's quite easy. If it's a trapezoid, you want to do it in 2 pieces. And so that's where down here, I say it may be at 1/2 of the height. So that would be for any time it's a constant pressure. Then it will be at h/2. So, and I think that's just about where we're finished. I got one more here. Probably don't have a lot of this, but we might, depending on your actually depending on some of your buildings. So we're dealing with structures that have a rigid diaphragm. We're not doing wood construction. So if you had, 3 walls, here it would be shear walls. Gosh. That's what it does, doesn't it? And the base shear would be distributed equally between them. So the force on each wall, if you ended up with a structural system where you had elements that were, let's say, twice as long on the outside, so the load would be distributed proportional to the stiffness. So walls these are the same thickness is the other caveat here. These all have the same T value. If it wasn't sad, it would be funny that it does that. So actually, yeah, that's what happens is my computer starts to warm up and it doesn't like the connections. I'm pretty sure that's what it is. That's why it starts out fine and I think it starts to go on us. But all right, well, anyways, we're right at the end here. So the distribution of how much force goes to each wall is proportional to the stiffness. So there would be 40%, 20%, and 40%. So just kind of keep that in mind. And right, the general systems would be concrete shear walls, brace frame, which would be steel for the most part. And then moment frames that could be either concrete or steel. So with that, I will do this with you. So I'm gonna take a 5-minute break. So at 5 o'clock, I will put you in your room if you'd like to break out with your partner. Well, actually, what I'll do is I'll do it now. I'll start to do it. And if you guys would like to work, ask questions, do that between 5 and 6. If you don't, if you're done, that's fine. You could work on homework 3 that's sitting out there as well. And but it's up to you guys. So I'm going to stop the recording. Stop share. Stop recording.